Why is creep a thermally activated process? Have you ever wondered why some materials seem to slowly deform over time when subjected to constant stress? This phenomenon is known as creep, and it is closely tied to temperature. Let's break down why creep is considered a thermally activated process. Creep occurs when materials experience time-dependent deformation under a constant load. This process relies heavily on atomic movements within the material. At elevated temperatures, typically above 40 to 50% of a material's absolute melting temperature, atoms gain enough energy to move around. This movement is essential for the slow deformation we observe as creep. As temperature rises, atomic vibrations become more intense. This increased energy allows atoms to diffuse through the crystal lattice or along grain boundaries more easily. Two main mechanisms are at play here: dislocation climb and diffusion creep. Dislocation climb involves dislocations moving out of their slip planes by either absorbing or emitting vacancies. On the other hand, diffusion creep involves atoms migrating to accommodate the deformation. Both of these mechanisms are thermally activated, meaning they requiring heat to occur. Let's look at diffusion creep more closely. In this process, atoms either move through the lattice or along grain boundaries. This movement requires thermal energy to overcome energy barriers. As the temperature increases, the creep rate also increases, making materials more susceptible to deformation. Dislocation motion is another critical aspect of creep. Dislocations can move via slip and climb, but dislocation climb is particularly dependent on temperature. This movement requires atoms to diffuse, allowing dislocations to bypass obstacles. At lower temperatures, this process is much more challenging, leading to less creep. Grain boundary sliding also plays a role in creep. At higher temperatures, grain boundaries can slide past each other more easily, aided by the diffusion and dislocation activity. This sliding contributes to the overall deformation of the material over time. The activation energy for creep is closely linked to the energy required for atomic diffusion. This relationship confirms that the mechanisms enabling creep are indeed thermally activated. From a mechanical failure standpoint, understanding this thermal activation is vital. Materials exposed to high temperatures and stresses, such as turbine blades or engine components, can experience creep deformation. Over time, this can lead to mechanical breakdown. By recognizing how temperature affects creep, engineers can design materials that withstand long-term loading at elevated temperatures. They can select alloys with higher melting points or microstructures that slow down diffusion and dislocation movement. In essence, creep is a thermally activated process because the atomic movements that allow for time-dependent deformation requiring thermal energy. This connection between temperature and creep rate is key to predicting and preventing mechanical failures in high-temperature applications.